The work of a group of scientists from the Institute of Continuum Media Mechanics, Perm, Russia, concerns the experimental study of dynamic deformation processes in main gas pipelines. The main gas pipelines are actively used now. They are the structures of high-risk class, which require special attention to their mechanical conditions. The peculiarity of these objects is their large extent and inaccessible location. There are many factors that can significantly affect the working condition of the pipeline. It may be accidental or intentional damage to the pipeline, problems in the operation of valves, occurrence of defects in the pipe due to corrosion, and so on. One of the most effective ways to ensure gas pipeline safety is to use automatic deformation monitoring systems based on fiber optic sensors. Such systems are energy efficient, economical, and quite unpretentious in maintenance. The development of such systems requires full understanding of the basic laws of dynamic deformation processes arising from the interaction of a metal pipe with gas flowing in it and ground layer, through which the gas pipeline runs. This knowledge allows us to determine the structure of the monitoring system and also to evaluate the sensitivity of the sensors to various mechanical impacts and damages. Development of monitoring systems requires a combination of numerical simulation approaches and experimental studies. Experiments are extremely important both for understanding deformation processes and for verifying the corresponding mathematical models. Our work is devoted to experimental research, and the object of study is a part of an existing main gas pipeline. A fragment of this pipeline is presented in the photo. The main technical characteristics of the pipeline you can see on this slide. Our attention is focused on the analysis of wave vibration processes occurring in a gas pipeline in response to various external actions, impacts on the pipe and ground surface near the pipeline, shutoff valves, gas leaks from the pipe. This slide represents an outline of an experiment. The figure shows the configuration of the pipeline section, the main equipment and sensor location. The study of vibration processes in the pipeline was carried out using fiber optic Bragg sensors. The parameters of sensors and equipment for data acquisition are shown on the slide. One component accelerometers record vibrations of pipe wall in the longitudinal direction, compression waves propagating along the pipe, and in the radial direction, bending waves. Accelerometers are combined with an optical fiber into a single sensor system. Data collection and initial processing are carried out online. The next slides demonstrate the experiment devoted to the study of the vibrational response of the pipeline to the impact applied directly to the pipe wall. Here, the experiment is demonstrated in which an impact was made to a pipe in the area where the pipeline was not immersed in the ground. The nearest accelerometer, located at a distance of 30 meters from the impact point, recorded the vibrational response of the pipe wall. The figures show the wavelet spectra of the vibrograms obtained by the S sensor. It can be seen that longitudinal vibrations with a dominant frequency of 100 Hz and bending vibrations with a dominant frequency of 200 Hz are realized in the pipe. We observe fast decay of vibration, and the S sensor, located 770 meters from the impact point, did not detect vibration response. This slide represents an experiment in which impacts were made on the ground directly above the pipe, buried in the ground by 2-3 meters, as well as at a certain distance from it. Impact points are shown in the diagram. An example of a vibrogram obtained from the sensor located on the pipe wall is shown on the right. As the experiment shows, an impact on the ground in the vicinity of the pipeline provokes pipe vibrations with dominant frequencies of 50-100 Hz. The intensity of these vibrations decreases rapidly with increased the distance from the point of impact to the sensor. The graph shows the change in the damping coefficient K, with a change in the position of the impact point. This coefficient is the ratio of the acceleration amplitudes obtained when the impact point is at a certain distance from the sensor and directly above the sensor. The decrease in vibration intensity occurs differently when the striker is displaced along the pipe or when it moves away from the pipe. But in both cases, when the point of impact is located at 25 meters from the sensor, the acceleration amplitude decreases by 100 times. Looking at the graph on this slide, we can make sure that already at a distance of 100 meters from the point of impact the accelerometer does not detect the vibration response. Vibration response to the ground impact has frequencies in the range of 10–150 Hz. As the distance from the excitation source to the sensor increases, the upper boundary of the spectrum is shifted to the region of lower frequencies. At the next stage of the experiment, the vibrational response of the pipeline to switching shutoff valves was studied. When the shutoff equipment switched, pressure jumps in the pipeline up to 3 atmospheres were recorded. The dominant vibration frequencies decreased with the distance from the source of disturbance. The dominant frequencies were recorded from 300 to 120 Hz. This slide shows vibrograms and the corresponding wavelet spectra obtained from the sensors located at different distances from the shutoff valves. As we can see, high-frequency vibrations decay more intensively. In our study, we tried to find out whether our monitoring system is capable to detect the occurrence of damage in the pipeline through which gas leaks. For this reason, a special plate with holes of various diameters was installed in the shutoff unit. Gas passage through this plate simulated gas leakage through the damage in the pipe wall. The vibrational response of the pipeline to this effect was recorded by the accelerometers installed at 3 points of the pipe. Additionally, sound signals accompanying the gas outflow through the hole were recorded. To register them, a microphone and equipment for digitizing and recording sound were used. Here we can see the Fourier and wavelet spectrum of an audio signal recorded over 3 seconds. The sound signal has the highest intensity is in the frequency range of 5–7 kHz. The spectrum also contains frequencies below 1.5 kHz, which can be fixed by a fiber optic accelerometer located on the pipe wall. The bottom figure shows the wavelet spectrum obtained using an accelerometer located at a distance of 110 meters from the signal source. Intense short-lived vibrations with frequencies of 0.8 kHz and 1.1 kHz are clearly visible on the figure. They correspond to the moment of opening the hole. But we can also note the presence of long-lived vibrations with a frequency of 0.27 kHz. The occurrence of gas leaking causes pressure variations in the gas pipeline, provoking low-frequency gas oscillations, which in turn excite the pipe wall vibrations. These vibrations were recorded at a sufficient distance from the hole. So, the accelerometer S3, located at a distance of 110 meters from the hole, detected vibrations with a frequency of about 280 Hz, which occur as a result of hole opening. The table shows how the vibration response of the pipeline changes when the size of the hole varies. As our experiments have shown, vibration sensors are sensitive to the appearance of a hole with a diameter of at least 10 mm. In the steady-state regime of gas outflow, Vibrations were recorded if the hole diameter was at least 50 mm. Remote sensors S1 and S2 did not detect the gas discharge through the holes of any diameter. Based on our experimental studies, we made the following conclusions. Application of external impact loads to a pipe wall or surrounding soil causes pipe wall vibrations in the local region near the impact site. The frequencies of vibrations are up to 1 kHz and they quickly decay due to energy dissipation into the ground. The size of the sensitivity zone of the accelerometer at the impact on the ground with a striking energy of 320 joules is ~60 meters. The operation of shutoff valves gives rise to low-frequency gas oscillations, frequency range 0.1 kHz, which propagates over a distance of more than 2 kilometers. The occurrence of such oscillations is due to the acoustic conductivity of gas. These oscillations can be detected by accelerometers located on the surface of the pipe. The occurrence of gas leaking from the pipeline through the openings with diameters of 2 to 50 mm leads to the pipe wall vibrations in the frequency range of 0.8 kHz - 8 kHz. The intensity of vibrations depends on the dimensions of the hole. These vibrations are recorded at a maximum distance of 100 meters from the hole. The obtained information is essential for the development of the automated systems for deformation monitoring of gas pipelines. It is used to evaluate the parameters of primary sensors, to determine the characteristic distance between the sensors, to identify the parameters of external actions, provoking the pipeline vibrations. Thank you for your attention.